I think my talk is going to be a bit more technical, so just please bear with me with it. So this workshop is about 3D digital twins. So I just thought, last night, let me just do a Google image search for 3D digital twins and see what comes up first on the first page. So here you can see that actually most of these models and applications are related to architecture, buildings, and also computer-aided design. And up there, you see that there is certainly an application with robotics. Now, robotics, I actually think, is actually the future. So I was raising my hands there, I was being asked, am I doing something in robotics? Now, you think about robotics, actually robotics, the robots themselves actually were all designed using CAD tools mostly. And then it wouldn't be very hard to imagine that if you're doing robotics or collaborative robotics, and the whole thing probably should be executed or modeled or simulated in a CAD environment. So what is the most popular 3D representation, say, in the past 2 to 3 years? I think arguably it's 3D Gaussian splatting. You actually heard about 3D Gaussian splatting over and over again in the first 2 talks. But I would argue that 3DGS, just like NERV, is actually not a modeling primitive. It's a rendering primitive. It was designed for novel view synthesis. So here is something, I may meet some skepticism, but this is what I truly believe. So this is mobile NERV. If you remove the texture, what you're left with is just a polygon soup. So Gaussian splatting 3DGS is very similar. So what's wrong with them? So first of all, they are unstructured. I think humans perceive the world in a structured way, but 3DGS and NERV, they're actually unstructured. 3DGS is even unbounded, right? You just have these Gaussian splatting. The Gaussian actually doesn't have a boundary. In fact, there's not a canonical or mathematically precise way of defining what is the object surface given a 3DGS. They're not easily editable, not easily reusable, and they don't easily support functionality, which I think is very critical for 3D digital twins. Now, there have been some recent attempts on improving 3DGS. One of them is 2DGS. Because of the multi-view inconsistency in the 3DGS, the idea is actually to have a surface-based splat. And this is using, I would say, a surface bias, thinking that most of the objects in the world are formed as surfaces, and we actually only care about the surface characteristics of these objects. And the other, this is actually, I think, is more recent, is Lin Pren is trying to fix the issue of unboundedness of 3DGS using bounded, more classical graphics primitives, in this case, octahedron and tetrahedra. But now if you actually look closely, the geometry is actually not reality, right? The geometry is actually formed by this polyhedra. They have this really rough surface, but when you render them, it looks great. So this, again, the purpose here is differentiable volume rendering. The geometry itself is actually not a replica or twin of the 3D reality. So I believe the key requirements for 3D digital twins, accuracy for sure, but we should go much more beyond the appearance. We need to focus on accuracy in terms of geometry, physics, and also function. And it needs to be simulation ready. It needs to be easily edited. It needs to be easily interacted with, because that's what real applications demand. So those are the 2 things I first thought about. And then I Googled, and these are many, many other requirements for the digital twin. There's actually from the AI answers, things like, you need to have a bidirectional communication, real-time data integration, et cetera, et cetera. So now if you go back to that slide, I showed a complaint about 3DGS and also NERV, that there are these issues on unboundedness, this and that. Now, let me just do something fun. I'm going to reverse everything. Okay, something structured, bounded, more editable, more reusable, and easily support functionality or functional reasoning. I would say these are all actually key characteristics supported by CAD models. So CAD models have structural regularity, symmetry, coplanarity. The reason being that these are there because they need to be used, right? If you do a 3D gen model where the chair needs to stand, which means that the 4 legs need to be coplanar. Actually, this is not an easy problem. If you take any of the state-of-the-art 3D gen methods, actually the chair actually is not necessarily able to stand. There's also the geometric regularity, sharp edges, corners, and parametric representations. And there's a famous saying in architecture, form ever follows function. So there's a strong tie between form, which is the geometry, and also the functionality. This was mainly referring to architecture, but I think it's really applicable to many more kinds of objects in our 3D world. And also, of course, CAD models are strongly tied to manufacturing and design. In terms of function, I just want to take a note that both the exterior, which was usually get from scanning, and also the interior, which are actually much more difficult to acquire, they are also very, very important for supporting the 3D digital twins. And most of the CAD models were made by pre-built primitives, right? They're like surfaces of all kinds, planes, quadrics, and I'm going to go through those things. So the question I want to raise is, how have the neural 3D representation, which is a popular topic in the past 5 years or so, how have they evolved to support CAD modeling? So I'm going to go through kind of like a quick evolution, pre-2018. Most of these representations, like arc trees, meshes, multi-view CNNs, and also 3D again, they were low-level primitives, not with a focus on CAD. And something happened. I think all 3 papers were published in CVPR 2019. That started kind of, I would say, neural fields, right? So the first paper was actually from SFU, my student and myself. We got IMNet. And then what happened? ECCV 2020, NERV happened. But NERV remained to be a coordinate-based representation. And then quickly, 3DGS, SIGGRAPH 2023, and then it turned from a volume-focused representation to a point-based representation, but they remain low-level representations and structured. So myself and my group, we didn't kind of follow the NERV and the 3DGS trend. We had a whole different path. After IMNet, we immediately switched into thinking about structured representation. So I'm going to go through most of these works fairly quickly. But why do I care so much about structure? Because structured model mimics human perception. This was a very old paper from, I think, the journal called Cognition. It says that for the task of visual recognition, essentially people see parts and use their relations, index into our memory, and then perform recognition. So structured model reflect our perception of the world. In a learning context, it really facilitates transferability, and in practical application, it facilitates editing and reusability of structures. The models are actually, I think, are very important. And also structures are strongly tied to functions. So this was a quote from one of the prominent papers in CVPR, I think it's 2011. Some people may know it's called "What Makes a Chair Chair." There, there's this quote called, "There's little we can find in common to all chairs except for their intended purpose." So I actually went really seriously going back to whether the quote was actually accurate and which book it was from. It was from this 1986 book called Society of Minds by Marvin Minsky. Some people refer to him as the father of AI. And then, indeed, there was this quote, and right after that, Minsky emphasized the importance of having structure descriptors and function descriptors for objects. And these two are actually strongly tied as well, because we care about how we do things, not just how we look at and how things are being visualized. So objects, functions, and the structures are related because functions are predominantly performed by the parts, and the relations between the parts actually matter for function. If you look at the example here on the left-hand side, the only reason that the chair on the left is functional and the right is non-functional, they have actually same number of parts and connections. It's just because the angles are not right for the one on the right, so that doesn't function as you see it. And also the manifestation or realization of the functions is often through part motions, which are also very important for any digital 3D digital twins. So now I'm going back to this kind of path of evolution from IMNet, which we started at CVPR 2019, and I can trace our kind of history, how we're going about structured CAD representation. So just a brief primer on IMNet, very, very simple. So the goal here is to learn a mapping from a coordinate x, y, z, given a shape code to occupancy. And then the network here is as simple as it can get. It's a 5-layer MLP. And in the end, you use supervision to produce, to try to reproduce the occupancy. Now, after IMNet, the first thing I gave myself is actually the same student who did IMNet was, can IMNet be modified to learn shape parts? Actually, before that, I always on structured modeling, segmentation, co-segmentation. So that was the task assigned to the student. And he gave me kind of the simplest possible modification to IMNet. All he did was to change the last layer of the network into a branched layer, right? So that's the only thing that has changed, actually, if you can see. And the hope was that we were hoping that each branch is going to learn a meaningful object part, right? And then other than that, it's all exactly the same. Input is the same, and output is the same. There's reconstruction loss per voxel. It turned out it worked pretty well. Of course, I'm going to explain why it worked well. So as you can see from this example, each layer actually learned a part. And then the application was co-segmentation. You have the same category of models. You want to have a consistent segmentation across, and we can do this without any supervision. Or you can actually just give one or few samples and then just add to the reconstruction loss and also label reconstruction loss. And you're going to have this, you can call it one-shot or few-shot co-segmentation. And the reason it worked was you can think of this like Occam's razor or the notion of compactness, because we forced the number of layers to be very small. It actually is 2 fewer than IMNet, and also have fewer neurons per layer. This way, we force it to learn a compact representation. Is the compactness that force network actually to learn meaningful parts for each category. So to verify that, we showed we used a few 2D examples. This is one of them. And as you can see, each layer learned a particular pattern and then formed them in a different, compose them in different ways, and also tried other examples. And then because we only have 3 layers, right, we can actually visualize each of the activation methods and see what exactly was the network learning. So we observed that in the first layer, it seemed to be learning this linear ramp or gradient field. And then the second layer, it seemed to be composing these half spaces, and then the next one composed what was composing the previous layer. So there seemed to be kind of a gradual composition. So that was kind of the main idea for the next paper, which is to make that interpretability precise. Instead of just letting the network learn these, we actually force them to learn exactly. The first layer is going to learn the planes. The next layer is going to do intersection of this half spacing into convexes, and the next layer is going to learn union of the convexes, so you can form like more general shapes. And that's exactly what we did. Also very simple idea. Other than that, it's all the same. Same input, same reconstruction loss, and then we call this paper BSPNet. The funny thing was that BSP originally was supposed to stand for binary space partitioning. That's what the first layer does. And actually, we were lucky that the paper actually won the Best Student Paper Award as well for CVPR 2020. Same acronym, by the way. So specifically, BSPNet takes a fixed number of planes, in our case it was 4,096, and we try to reconstruct all the input shapes in the best way. And the plane parameters, ABCDs, are just going to be the weights in the network. And then the final outcome of this learning process, we're going to have a compact representation because there are very few planes. And these planes easily form sharp features. If you look at the result on the right compared to margin cubes, with the meshing of the neural fields, we got much cleaner for CAD representation. And that was inspiration for the next paper. So now we have planes, but planes are certainly limited, right? So now we're going to extend the planes into quadrics. So this we can actually represent more general CAD models. That was actually the idea. So the funny thing is, along the evolution, I think every paper can be explained just using one sentence. If you go from one to the next, you know the kind of context. So the next paper we call it CapriNet. We turn planes into quadrics. That's more general. And also we added a difference operation, right? Because as you can see, first when you have a union, and then you have, sorry, you first have intersection, you have a union. This sounds like CSG, which is construct solid geometry. And what's missing for a lot of the CAD parts is the difference operation. Because if you think of like these machine parts, sometimes the difference operation is very, very critical to get fewer operations. So that's all we did, extending planes to quadrics, and then add a difference operation, and then we got CapriNet, and it's able to produce much more reasonable interpretation of CAD models, especially those from the so-called ABC dataset. So that's CapriNet, and then with this kind of representation, then you're able to edit easily because you have a CSG. You can just change parameters so you can get new models. And also compared to BSPNet, the CapriNet is able to get more reasonable interpretation for a machine part because of the difference, also because of the quadrics. However, if you look at the result of CapriNet, these primitives still don't seem to be very reasonable, actually highly implausible. So even though we don't have supervision, which is good, but the problem with the CSG is that number one, you don't have unique solutions, right, for the same shape. Number two, it's still based on point clouds. So we're trying to kind of fix this too. This was the first issue, trying to fix the fact that in the point clouds, but everyone was working a multi-view or single-view image to 3D. So that was the next work, ECCV 2024, where we were able to just take 3 white baseline images and produce a assembly, a CSG assembly. So we call this DPA, stands for differentiable primitive assembly. The key idea really was to take a pixel nerve as the base, and we'll switch off the density estimation using our differentiable primitive is actually more or less from a CapriNet. So we're able to take 3D images, no 3D supervision, and we're going to get a assembly, and then with texture, you can do editing directly on the output. So as I said, the other issue with CapriNet with this CSG operation is that even if you have the same ground truth shape, you have an infinitely many number of ways you can actually construct it, right? If you just want to take away a cylinder from a shape, the cylinder can be arbitrarily long, right? This is actually what's happening, as you can see on the right. So how do we fix that? So we kind of, starting from maybe 2023-ish, we switched to another de facto representation in CAD, which is called a BRAP, or boundary representation, where it's forming a CAD shape using surfaces, curves, and vertices, right? Instead of using this by union and intersection operations. This is also a structured and compact representation. Before our work, which I'm going to present on the next slide, all the previous BRAP constructions were local and bottom up, right? So they have certain of their limitations, including ransack, point clustering, also BSP. So we first realized there is a challenge with BRAP reconstruction, say from point cloud. That is, you have 3 questions that you need to answer. The first question is how many primitives, and what are the primitives, and how they're connected. So 2 of them are actually discrete or topological. The other one is continuous. To mix them together, it's going to make the problem challenging. And this is what most of the other works were facing. The solutions we developed is actually one of my favorite papers, by the way. It is called the split and fit. The key idea is that we're going to learn BRAP implicitly. We do not directly get the primitives. We instead try to learn to construct first a spatial partition. In this case, it's a Voronoi partition. So after we get a partition, that's actually the only learning part. With a partition, everything else comes pretty easily. So the first step is actually the split or the partition, and the second step is to get all the primitives. Okay, so we don't get primitives first, we get partition and then primitive. Why is that a good idea? Because, well, by the way, the Voronoi diagram is only one that we predict. The first good thing is that it's unique. Given a BRAP, there's a unique Voronoi diagram. Unlike CSG, there are infinitely many ground truth solutions for CSG. And second of all, after you get the Voronoi partition, you already know how many primitives. That's the number of partitions, or number of cells. And also you have the connectivity, right? That's actually also given naturally by the Voronoi diagram. Okay, so there's no separate topology prediction. So again, the difference between bottom up is you get the primitives first. You have to worry about how many, where they are, and how they're connected. But we just get a partition. We'll get everything else naturally just from the Voronoi partition. So I'm not going to really show any like qualitative results. Of course, it beats most of the the baseline is also highly generalizable compared to state of the art. Now, next, we want to do BREP generation in a multimodal manner, right? So that I believe this is the very first work that allows you to go from, doesn't matter what, text, single view, multi-view, sketch, or unconditioned, to generate BREPs of very, very high quality. And this is work we're going to be presenting at CGRAPH in Vancouver. So the key idea, there's some similarity to split and fit, is that all the previous generators were separate. They have surface generators, curve generators, and vertex generators, and they also have to worry about the topology. So we have a holistic latent representation that is only based on surfaces. That is, you only need to learn to generate surfaces, and then curves, they're just intersections between surfaces, and then vertices are just intersections between curves. That was something like a very simple idea, but it worked. So instead of predicting everything separately and then also worry about topology, we just predict surfaces, and we use a neural intersection module to get the curves. And finally, I'm going to talk about just one other piece of work. This is actually a work we're going to be presenting tomorrow. It's a CVPR highlight. It's also a CAD generation, except it's for architecture. So I want to bring to attention the use of CAD programs. Okay, I think that's a really very promising way of learning structured representation using CAD or architectural programs, because the programs, like languages, they are intrinsically structured, right? And also, you can easily embed your inductive biases into priors for either CAD or architecture. Finally, because program generation is basically about next token prediction, you can actually utilize the power of the modern day transformer models. So this is work we call ArcPro for architectural program, and then you can actually take a very sparse, noisy, incomplete point cloud and get a good 3D abstraction all through a domain-specific language that we developed for this kind of task. So this is the poster. Tomorrow, the student unfortunately is unable to come because of visa issues. I'll be the one standing there, so hopefully I'll see some of you tomorrow, 4 to 6. Okay, I'm concluding. So I believe parametric curves and surfaces, planes and quadrics are more suited as modeling primitives compared to low-level primitives such as linear prims, octahedra, or points or voxels. You saw CSG and BREP as structured compact representations. They support editing, primitive reuse, and also functional reasoning, especially suited for 3D digital twin applications. And all the works are presented are differentiable. As you are able to parameterize your representation, you can find ways to make it differentiable. And you can do this either from point clouds, also from multi-view images, single-view images, and later we showed with holistic latent representation, you can also do this from text. But still, I want to mention, this is only at object level, right? You've seen the results, demos from the previous two talks at a much larger scale. I think it's still highly, highly challenging to go for a CAD modeling, right? I think it's possible, and also think one promising path of exploration is actually use architecture or CAD programs. I think the scalability there is likely to be better. There are other challenges. I haven't touched things like symmetry, copularity, or other engineering constraints. I think they're actually more difficult than the constraints we are able to handle so far. Functions. Most of the 3D models you see, right, actually lack function. They actually lack motion. And most of them don't have any interiors, right? So what this means is that you can actually only look at them, right? If you go into a room or go into an office, you try to open things up, there's nothing inside. It's all empty. So that actually makes most of these digital models kind of useless, right? They can only be looked at, but you cannot really be used, cannot really function the way that they need to function. So I only know probably 2K models that have interiors, the one with motion. Just check how many models in Objectverse XL, 10 million, actually have motions, right? So there's actually a lot to do to add motions. I believe the next talk is about motion dynamics, which I think people can learn a lot what's happening. And I advocate a robotics project, which we call active 3D reconstruction. We have robots that go around and interact with objects, scenes, open things up, and scan both the inside and outside, right? So this way you can actually get both motion and interiors acquired together. And this is definitely a really good direction to go into that combines graphics, vision, and robotic. High naturally is actually, I don't think robots can actually open everything, but that's the direction I want to advocate. Okay, that's all. I hope I'm not going over time.
No.
Okay, thank you very much.